My name is Andre. I'm a PhD student at Trinity College Dublin under the supervision of Professor Luis DaSilva. And today I'm going to present a work we have conducted on network sharing for reliable communication. This work was conducted in Connect Center, the Irish Research Center for Future Networks and Communications, and also within the Satori project, a joint collaboration between Trinity College Dublin and Tsinghua University. The main motivation for this study is the emerging number of critical communication-like applications, such as factory automation, public safety, and cloud gaming, which have very stringent requirements in terms of communication, requiring reliable and resilient communication. Reliability usually comes at the cost of extra resources being made available, such as in the form of multiple antennas, multiple connections, or denser network deployments, which naturally increases the expenses on infrastructure and for the mobile network operator. An alternative to minimize the expenses while meeting the reliability requirements is network sharing. Network sharing can come in different flavors, such as neutral hosts, where operators they share a common infrastructure, and also multilateral agreements, where operators they serve each other's users. In this paper, we are going to focus on a kind of the second type, and particularly, we are interested in network sharing in the form of multi-operator connectivity, where mobiles they are allowed to parallel connect to different mobile network operators. This system is shown in figure 1, where the mobile has multiple radio frequency front ends, each of which can connect to a different mobile network operator. And we assess the performance of the system by looking at the overall channels capacity as a figure of merit. And we analyze 4 different strategies here. We analyze the first one, that it's the single operator, where there is no combining of those multiple connections. And we also analyze 3 other strategies where we combine the connections of multiple connections. So in order to assess such a system, we make use of a data set of ours that consists of signal level KPIs of 3 different mobile network operators at the same times and same locations. We use the SNR to compute the overall channel capacity I have just mentioned. So this figure illustrates the locations of our data. We have traces for 3 different regions in the city of Dublin, Ireland. And the intuition behind benefiting from multiple connections comes from the redundancy and the complementarity of different mobile network operators. By combining signal from multiple operators together, most gains in reliability arise when a given operator is capable of providing connectivity when another is not. So to illustrate that, we plot this figure that represents the lowest 5 percentile of SNR values of each of the operators from our data set. So each color represents a different operator. There are regions, as the one circled in the middle of the figure, where we can spot 3 different colors, meaning that in that specific region, we have low SNR values for the three of our operators, meaning that in that region, all 3 they underperform. However, if we look at the overall picture, we also see regions as the one pointed by the white arrow, where we only have the operator in red underperforming. That means that in that specific street, a mobile connected to multiple operators could benefit from connections from operators in blue and yellow to supply connectivity while operator in red underperforms. So that's the intuition behind using multi-operator connectivity, exploiting the complementarity of of different operators to keep a reliable communication. So now we look at the data of that same region we analyzed before, but harder than looking at the 5%, the lowest 5% SNR values. Here we look at the overall data. So the interesting information here, we plot the probability density function of the channel capacity in figure 4. The interesting information here is how combining techniques suppress the lower tail of the probability density function by, by comparison with single operators. So the lower tail for the single operator, it's quite a heavy lower tail, meaning quite many data points in our data set. They have low channel capacity, but by combining multi-operators together, we have that this lower tail is mostly suppressed and the overall shape of the density function is preserved. This is good news because when we talk about reliability, we are mostly interested in getting rid of the periods of shortfalls or periods of poor connectivity, and that's exactly what we are getting here by combining multi-operators together. So in order to quantify the gains in terms of reliability or how much we suppress the lower tail of the PDF, we use a metric called the superquantile. Superquantile comes from risk evaluation, and it's basically a measure of the lower tail of the probability density function. Superquantiles have this parameter alpha, and alpha is basically a parameter that specifies which part of the PDF we are looking at. So by setting alpha to 1, we are basically interested in the region of the lower tail. And when alpha approaches 0, we are looking at the overall data, the overall probability density function. Particularly if you set alpha to 0, it means that the superquantile is equivalent to the average. So here in this graph, we compute the superquantile and the average of the of our figure of merit, the channel capacity. And we compare the gains in performance in terms of superquantile and in terms of the average performance. Each graph represents the channel capacity of each of the 3 regions of our data set. The first pairs of bars, they correspond to single operators functioning alone. And the last set of bars, they correspond to the multi-operator connectivity techniques we are analyzing in this paper. The interesting information here is that it's the delta gain between single operators and multi-operator modes. So to compute the delta, we have those lines. By the way, the orange bars, they correspond to the superquantile, and the blue bars, they correspond to the average. So the delta in gains, they are depicted by the lines we have in the graph, where the dashed lines, they represent the best performance of single operators working alone, and the continuous bars, they represent the best performance of multi-operator connectivity, both for superquantiles, the orange lines, as well as for the average performance. So we see that the delta in terms of the superquantiles, it's almost 1 order of magnitude, meaning that the gain in terms of the superquantiles, the gains in terms of suppressing the lower tail of the PDF is almost 1 order of magnitude. On the other hand, the gains in the average performance, they are much more modest in this case. And this means that the gains of multi-operator connectivity are much higher during periods of shortfalls than in the average periods. Those gains, they do not come for free. They have a cost. And for example, by using 3 connections, we use 3 times more bandwidth than in a single operator. Here in these graphs, we analyze the cost of multi-operator connectivity by estimating the expected coefficiency. Recall that when we set alpha to 1, we look at all data we have, we look at the entire region, and we basically look at the average performance. And so here we see that, for example, in the average case, the single operator, the blue dots, they are twice more efficient than the combining techniques. Meaning that in the average case, multi-operator connectivity comes twice more expensive or twice less efficient than single operator connectivity. However, when we focus our attention on periods of shortfall or connectivity shortage, meaning that we are setting alpha to 1, the cost of multi-operator connectivity is basically the same as single operator connectivity. So it means that in the average case, multi-operator connectivity is quite inefficient or costly, but during periods of shortfall, having multi-operator connectivity comes at the same cost as single operator connectivity. So we have this interesting trade-off where the gains of multi-operator connectivity, they mostly lie in periods of poor connectivity by comparison with single operators. The gains, they mostly lie in periods of poor connectivity by comparison with the average case. And the cost of multi-operator connectivity, it's quite high in the average case, but comes at the same cost as single operator in the periods of shortfalls. So here we have analyzed network sharing in the form of multi-operator connectivity as an alternative to cope with the increasing demand for reliability. And we have also drawn these conclusions about the gains where they are higher, when they are more significant, and also when they are costly and when they come at lower cost. And the conclusions here is that the gains, they are usually higher and less costly in terms of during periods of connectivity shortage. And for that reason, the results, they also motivate the investigation of multi-operator connectivity as means of design reliable networks and means of allocating multi-operator connectivity resources when they are needed and avoiding the average case of allocating such resources when they do not bring that much benefit. Thanks.